Here are today's objectives. We want to understand edge and screw dislocation motion from an atomic perspective. We want to understand how plastic deformation occurs by the motion of edge and screw dislocations in response to applied shear stresses. Understand the sleep system. Today's lecture is very important for you guys to understand the plastic deformation in metal microscopically, and we have plastic deformation if the applied load reaches the yield stress. And however, today's class will give us an opportunity to see from an atomic perspective and how the plastic deformation occurs. So I'm very interested in today's lecture, and so this is the following the quiz, and you might need to answer several questions based on what we have learned today. So to have a better score for today's quiz, and I want you guys to pay attention to what I say. If you have any questions, you need to ask me before this lecture ends. Let's get started. Um, so today we talk about dislocation motion and plastic deformation, and here we focus on the metals. For the metals, plastic deformation occurs by slip. Here is one word, slip. A slip means that edge dislocation. This one is extra half plane of atoms slides over adjacent plane, um, half plane of atoms. So you can see, and I want to show you guys here. You can see here. So this is on one plane. So this is plane B, the plane C, and the plane D. And however, in front of plane B, we have a half plane which takes the place, which is denoted as the half plane A here. So this plane, will be called slip plane. So this is a edge dislocation line. So this is edge dislocation line. Suppose you apply the shear force on the atoms, and then so what will happen? So here, okay, so this part 1 2 3, so this is the three lines. I said three lines, that is in the direction that is perpendicular to the screen here, okay. And so when we have this applied force here, so these three guys will be connected, okay, will be moved from this original position to here. As a result, so these three atom lines, as I said, and it is perpendicular to the screen. So this is the three guys will be connected to this 1 2 3. So as a result, we will this A plane will become from a half plane here to a whole plane, go this way. And however, the original and the three lines of atoms 1 2 3 on plane B and will move or will becomes will have this form, will take this form here. That means, so we can see this is these three guys and these three guys, and you can just assume, and so these three guys are moving from left to right. And so you can see here, okay, so if we keep applying the shear stress, and so finally, so this half plane will come out come out to this position, to this position. So this is a unit step of slip. So this is one step. That means from here to here, how many steps we have? 1 2 3 4. I'm sorry, 5. 5 steps. Um, and so this is a dislocation motion along the slip plane in a slip direction perpendicular onto the dislocation line. The sleep direction is the same as the Burger's vector direction. Uh, Burger's vector direction. You can see, and you can recall, we have two different major kinds of dislocations. One is called edge dislocation, and one is called screw dislocation. Screw dislocation as a direction of motion, it is rotating. It is rotating. And edge dislocation, it is this is a translation. And so you can see for the figure A and figure B, and we can see the difference between edge dislocation and screw dislocation. For the deformation mechanisms, there are several the concepts here. Sleep, the process by which plastic deformation is produced by dissolution motion. So this is a sleep. And sleep plane, the crystallographic plane along with the dislocation line, the transverse, is transverse. And dislocation do not move with the same degree of ease on all crystallographic planes of atoms and in all crystallographic directions. So what does that mean? It means that given a specific kind of metal and itself has its own favorable sleep directions and sleep plane, and which if this applied load reaches the yield the strength, the plastic deformation occurs. So be very, very careful. Sleep system. So you see this here is the very, very important concept, sleep system. A sleep system is a combination of sleep plane and sleep direction. First, you know the sleep plane. And on this plane, there are infinite number of directions. You should know these are sleep directions. Okay, you can see, yeah, sleep plane, plane on which easiest slippage occurs. Easiest. So that means to minimize the energy, to minimize the energy of the system. And if there is any deformation, and the deformation only occurs in a direction in which there is minimal energy is needed. So this is a universal rule of energy minimization for any kind of physical deformation, physical phenomena. Sleep directions, direction of movement and Hecke's linear densities, and along the Hecke's linear densities. So deformation mechanisms. Uh, so here, look at this picture, okay, this photo, this figure A and figure B. So here is, so in this is a plane here, okay, so you can see this is for A, okay, A 111, okay, so these planes is 111 and 110 and sleep system shown with the FCC unit cell. So on this plane, right, on this plane, either this direction or this direction or this direction, and physically these three directions are the same. And here it looks different because from our perspective, so our perspective means that, and they are different from our perspective, but physically they are the same because we artificially impose a Cartesian coordinate system x, y, and z. For this is a figure B, the 111 plane from A and 3110. This is in the planes here. 111. This is a 110, 110, 110. These three planes are exactly the same, are equivalent to each other physically. So as indicated by arrows here, you can see within that plane constitutes the possible sleep systems. Any questions so far? No question? And please keep in mind about what is a sleep plane, what is a sleep direction, and what is a sleep system. So they are very, very important concepts for you guys to understand the plastic deformation from atomic perspective. And as I said, you might see this question or questions, related questions um, in our quiz. So here is the deformation mechanisms. And so this table shows the slip systems for face-centered cubic (FCC) and body-centered cubic and BCC, along with hexagonal close-packed metals (HCP). Um, we can see um, metals here for this metal, and for this is three groups of metals. And for this first group, so this is FCC, right? So this is FCC cubic, and along this direction 111 slip plane and slip direction 110, right? And so here is the number of slip systems, and we have 12. We have 12 here. And for second group of materials, metallic materials, and they are body centered, the cubic. So for them, and uh, for different materials, for example, alpha iron, uh, tungsten, this is a molybdenum, and they have slip plane 110 and slip direction 1 bar 11. So this guy has 12. So these three guys, they have 12 on slip systems. For second one, alpha iron W, and so they also have 211, right? And we also have 211 slip plane and 1 bar 11, and on that direction, in this plane, we have 12 on slip systems. Alpha FE and the 321 and slip direction 1 bar 11 for these two guys, and have 24 on the slip systems. Uh, okay, so for the third group of materials, so hexagonal close-packed materials, I also have CD, xenon, magnesium, titanium, and this beryllium. So these is five guys, they have 0001, 1120, and they have three slip systems. For titanium, and they also have this one and these three. So titanium, magnesium, and they have these. This is slip systems. And one question I want to have, some students might ask, and Dr. Mao, for this alpha Fe, totally how many slip systems this material have? That's a very good question. For alpha Fe, they have 12 on this plane, and the same thing, they have 12 on this plane. And for same material, they have 24 on this is 3 to 1 on this plane. So that means for this alpha Fe, and they totally have 12 plus 12 plus 24 on 48 slip systems. So 48 systems. There is another conclusion. The more slip systems a material has, the much easier, the easier this material will have plastic deformation before it breaks. Did that make sense? So this is understandable. If there is more slip systems, that means if there is applied load, and if there is applied load, so this material which has more slip systems will have the tendency to have more directions to accommodate to this applied load. As a result, it is much easier for this material to have plastic deformation before it breaks. Does that make sense? So in our quiz, I might ask you, what is the relationship between the number of slip systems and the ease of plastic deformation or the ductility of this material. And you should be able to use your own words to tell me what's the relationship between the number of stable systems and the ease of which the ease for this material to have plastic deformation. Okay, everyone.